Hello students, welcome to lectures on complex numbers. In the last lecture we discussed the nth root of unities and based on that we have proved several identities. Let us continue on this discussion. So, let me recall the nth root of unity. It is a complex number satisfying the equation z to the power n equal to 1, and what we showed in the last classes, there are n distinct complex numbers satisfying this equation, which is namely given as zk, which is given by cos of 2k pi by n plus I sin 2k pi by n, k is from 0 1 till n minus 1. And we notice that these zk is nothing but z to the power 1 k. So, you consider k equal to 1, which is z1, that is cos of 2 pi by n plus I sin 2 pi by n. Now, take its power k, which generates the other nth root of unities, and for the convenience we will introduce the notation cis theta, which is defined as cos theta plus I sin theta, and if we take its power k just by de Moivre's law, we see that this comes as cis k theta. And let us make some remarks. What we observe is, if we consider, say, put alpha as z1, that is the cis 2 pi by n. If we raise the power n for alpha, what we get is cis 2 pi by n power n. By above rule, we see that cis 2 pi, which is nothing but cos 2 pi plus I sin 2 pi, which is 1. And if we raise the power alpha power k n, this can be written as alpha power n to the whole power k, and by above observation this is again 1 for k is greater than or equal to 0. Similarly, one can observe for k negative value, say for k less than 0, if we consider alpha power k and power n, and one can verify that this is again same as alpha power n power k, which is again 1. So, as a summarizing, the rule is, if we consider the alpha power multiples of n, that is k n, this is 1 for all k belongs to integer. And second remark, let us write down these nth root of unities, which can be written as alpha power k with k from 0 to n minus 1, or nth roots of unity, which means that it satisfies. So, it satisfies any alpha power k, satisfies the equation z to the power n will give us 1, which is same as saying that alpha power k is root of the polynomial z power n minus 1 for k 0, 1 till n minus 1. What we know is for any given n, 1 is always root for this polynomial, which can be easily seen. Consider z to the power n minus 1. This can be factorized as z minus 1 product with z to the power n minus 1 plus z to the power n minus 2 . So, by easy calculation we can verify that left hand side, that is z power n minus 1, same as writing in terms of product of these two factors. Now, since z equal to 1 is a root for this polynomial, we have factored out the term, and remaining factors, which is the n minus 1 degree polynomial. For this, the alpha k from 1 to n minus 1 will be root of this polynomial. That is, from the above observation we can say that alpha power k is root of z n minus 1 plus z n minus 2 plus z plus 1 for k from 1 to till n minus 1. So, it means that we can write the polynomial z power n minus 1 plus z power n minus 2 plus z plus 1 can be written as z minus alpha, z minus alpha square and so on, z minus alpha power n minus 1. So, if I write in a short notation, what we see is that the factor or the polynomial z power n minus 1 plus z power n minus 2 till this plus z plus 1, this polynomial can be factorized as using the nth root of unities power k, and the equality is easily argued because n minus 1 degree polynomial can have at most n minus 1 roots, and what we observed is n minus 1 roots we already observed, that is the distinct nth root of unity be roots for these polynomials. Hence, this polynomial can be factorized in this form. With this remark, let us move to a simple problem. Find the number of ordered pairs a comma b where a and b are real numbers such that it satisfies this equation a plus ib power 2016 equal to a minus ib. So, we are asked to find possible a comma b real numbers such that it satisfies this equation. What we know is given ordered pair a comma b, given a comma b in R2 Cartesian product of real numbers, we can associate a complex number a plus ib uniquely, which means that finding the ordered pair satisfying this equation, which is equivalent to find the complex number satisfying this equation because of this relation. So, consider z as a plus ib, and we are looking for all complex number z whose power 2016 should give us z bar. So, if we solve this equation for set of all complex number satisfying this equation, equivalently we can associate the ordered pairs a comma b satisfying this equation. So, let us solve this equation. From this equation, observation is, if we apply the modulus, we see that modulus of 2016 must be equal to modulus of z bar, which is same as mod z, which implies that mod z bring to the left hand side. So, we have 2016 minus mod z, this must be equal to 0. So, what we are arguing is, if there is a complex number satisfies this equation, then it must satisfy this relation. This implies that mod z product with mod z power 2015 minus 1, this must be equal to 0. From this relation, we see that either mod z must be 0 or mod z power 2015 must be equal to 1. So, we get the relation either mod z equal to 0 or mod z power 2015 must be equal to 1. If mod z equal to 0, it means that z is 0. So, let us consider if z is non-zero, then mod z power 2015 must be 1. From this we conclude that mod z must be equal to 1. Why? Because if mod z power 2015 is 1 and suppose mod z is less than 1, this immediately tells you that less than 1 or greater than 1, you immediately see that mod z power 2015 cannot be equal to 1. Okay. So, by this argument we can see that immediately mod z must be 1 if its power is 1. So, from this conclusion, so now consider the case for mod z equal to 1. If mod z equal to 1, then mod z square is again 1, and this will tell us immediately z bar, we can write mod z square as z into z bar, that is same as z bar is given by 1 by z. Now, under this case we see that we go back to equation, from 1 our complex number should satisfy this z bar. Now, we are in a case if mod z equal to 1, then z bar is nothing but 1 by z. So, this implies that z to the power 2017 is 1, and we know what are all the possible solution for this equation. This is nothing but the nth root of unity where n is 2017. So, it means that the equation 2 as 2017 distinct non-zero solutions and notice that we observed if you consider z equal to 0 also satisfies this equation. So, which means z equal to 0 is also solution 1. As a conclusion, equation 1 as 2018 distinct solutions. Let us see a nice property for nth root of unity. Consider the nth root of unity which is written as zk given by cis 2k pi by n, where k is 0 to n minus 1. Now, consider the sum with raising powers to nth root of unities by m, sum it from 0 to n minus 1, then we get the value as either n or 0. We get n if the power m is multiple of n, which is same as saying that n divides m. Otherwise, we get the sum value as 0. Let us prove this proposition. Zk, as we mentioned earlier, we can just write it as alpha power k, where alpha is cis 2 pi by n and k is from 0 to n minus 1. Now, consider the sum summation k from 0 to n minus 1 z to the power k zk power m, which is same as k equal to 0 to n minus 1, zk is replaced by alpha power k and power m, and this is same as summation k from 0 to n minus 1 alpha power m. Now, this is a fixed number with raised power k. Now, the sum is nothing but geometric sum. We know how to easily find the value of the sum. Maybe just as a remark, I will just add that geometric sum summation k equal to, so let us just recall geometric sum, let us say till n minus 1, we have a to the power k, the sum value is given as a to the power n minus 1 divided by a minus 1, where a must be not equal to 1. Okay. So, we can easily derive that the sum value was thus. We can apply this here, which means that the sum value is here a is the fixed value here alpha power m. So, we get alpha power m raised its power n minus 1 divided by alpha power m minus 1. Now, let me write the same sum value in the next page. Summation k equal to 0 to n minus 1 z power k power m, its value we found it as alpha power m power n minus 1 divided by alpha power m minus 1. Notice that the alpha power m will be equal to 1 if m is divisible by n. Okay. So, which means this formula is valid if alpha power m not equal to 1, and the equality happens when n divides m. So, if n does not divide m, which means m is not a multiple of n, in that case we know that alpha power m is not equal to 1, and the above. So, the expression k equal to 0 to n minus 1 z power k power m, we see that the term here, this is same as alpha power n power m minus 1 divided by alpha power m minus 1. And notice that alpha power n value is 1. So, this becomes 0, and this is non-zero quantity when n does not divide m, which means we get 0 if n does not divide m. Suppose n divides m, which means that m is given by some multiple of n. In that case, the summation k from 0 to n minus 1 z to the power k, we need to raise power m, which is q n, and we already noticed that nth root of unity, its multiple of n power will be always 1. So, this can be even rewritten as alpha power k, and here it is k q, and we easily see that this term is 1, and again if you raise power k q, it is again 1. The sum value is n if m is multiple of n. So, we have proved our proposition, that is, if you consider the nth root of unities, raise power m, sum it up all the nth root of unities, then you get value n, provided m is multiples of n, otherwise we get 0. Let us see a very particular case with m value as 1. In particular, consider m value as 1. Certainly, if n is greater than 1, it does not divide m. So, the sum value from k from 0 to n minus 1 z power k, where m is considered as 1, we get the sum value as 0. N is greater than 1. So, now write down what is this zk. Zk is nothing but cos 2k pi by n plus I sin 2k pi by n, this is equal to 0. And now we can easily see that real part of this complex number is 0 and imaginary part of complex number is 0. Calculate what is the real part of this complex number, which is nothing but k equal to 0 to n minus 1 cos of 2k pi by n, which is real part of this complex number, and this is 0, and the imaginary part, which is sin 2k pi by n, this is 0. If I write down explicitly, this is for k equal to 0 cos 0, that is 1, and then the remaining terms what we have here, it is 2 pi by n plus cos 4 pi by n until cos 2 n minus 1 pi by n, the value is minus 1, and we get another trigonometric identity with substituting k values. For k equal to 0, we see that the first sum value is 0, the remaining factors we get sin 2 pi by n, sin 4 pi by n, and the last term sin 2 n minus 1 pi by n, the value is 0. So, for the particular case power m equal to 1, we got a nice trigonometric identity. Let us do a simple problem based on this proposition. We denote alpha as cis 2 pi by n, it is nothing but the nth root of unity, and a complex number z satisfies following condition, that is, you measure the distance from the nth root of unity alpha k to z, which is less than or equal to 1, from all the nth root of unities. If there is a z satisfies this condition, then the z must be 0. So, let us try to see pictorically. What we see is that if k equal to 0, what you have is 1, say the maximum distance from 1 to z is less than or equal to 1. So, we know what is this distance, this is unit 1, the distance also here it is unit 1. Now, z is lies inside within the distance of 1 from the complex number 1. Okay. So, which means you trace the what is the length 1 from 1, then we get this circle. Now, z is somewhere inside, and now take another say alpha, which is in the nth root of unity. Now, you make another circle with the distance 1, again the z lies inside the circle. So, similarly you see that with each nth root of unity, the distance to that nth root of unity is always less than or equal to 1. If such a complex number is there, then we are going to show that it is nothing but the origin. Let us try to prove this result. Given to us, that is the z minus alpha power k is less than or equal to 1 for all values of k from 1 to n minus 1. So, now I just fix a value of k which is in 0 to n minus 1. Then we see that mod z minus alpha power k whose square, which is just the again product of each factor, and this term is less than or equal to 1, again this term is again less than or equal to 1. So, the product is less than or equal to 1. This implies, now try to expand this left hand side, this is z minus alpha k, z minus alpha k bar, their product is less than or equal to 1. Now, further expand left hand side, this is mod z square and the other terms z alpha k bar minus z bar alpha power k plus you get modulus of alpha k square, which is less than or equal to 1. Recall that it is nth root of unity which lies on the unit circle. So, which means modulus of this alpha power k value is 1. This implies that mod z square less than or equal to, I take all other terms right hand side, you get it is z alpha power k bar plus z bar alpha power k, where k values are from 0 to n minus 1. The same inequality satisfies. So, just observe what it means. You take k equal to 0, you get the first nth root of unity. For that particular complex number, this inequality is satisfied. K equal to 1, again the inequality is satisfied with, say, k equal to 1, you get alpha bar plus z bar into alpha. So, we get n inequalities. Now, you sum this n inequalities, this implies if I sum this n inequalities, left hand side I get n terms of mod z square, this is less than or equal to sum of k from 0 to n minus 1 z multiplied with alpha power k bar plus, this is a common summation, we can have it. Now, you need to apply the proposition which we have just now proved, that is the sum of nth root of unities is 0. Now, which is exactly the summation here. Here we can throw out z as a common factor and then you get on the right hand side, let me write out, this is less than or equal to z times summation k from 0 to n minus 1 alpha k bar plus z bar summation k equal to 0 to n minus 1 alpha power k, and we know that this sum is 0, and here the conjugation can be taken commonly outside to the summation, and the sum is again same as this, which is 0, which means the right hand side become 0. Now, see that the modulus of z square, which is a non-negative term, which is less than or equal to 0, it means that mod z must be 0, that is same as saying that z is 0. So, hence we proved our desired result that if there is a complex number with distance from all nth root of unities, which is with the distance less than or equal to 1, then the complex number must be the origin. Let us prove another nice result, that we are given a n regular polygon. Let us call it as vertexes, that is p naught, p 1 till p n minus 1, which is placed on the unit circle. Okay. So, we are given with the n regular polygon which is placed on a unit circle. With this given assumption, we are going to show that distance from p naught to p 1 multiply with distance from p naught to p 2 till the distance from p naught to p n minus 1, thus n terms you multiply, you get the value n. That is interesting identity. And moreover, using this identity we are going to derive nice trigonometric identity, which states that sin pi by n, sin 2 pi by n till the sin n minus 1 pi by n gives the value n by 2 power n minus 1. And similarly, we have one more identity. The difference here, we could see that here we have say odd multiple of pi divided by 2n. Instead of here we have consecutive terms pi, 2 pi. So, we have till n minus 1 pi by n, but here we have odd multiples of pi divided by 2n. Their product gives us 1 by 2 power n minus 1, which is very interesting identity. Let us prove this result. Let us try to see what is the problem which is given to us. We have a n regular polygon which is placed in a unit circle. It is like p naught and p 1 and so on, p n minus 1. We know that these vertex can be chosen as nth root of unity. Okay. So, without loss of generality, we can assume that the given n regular polygon is placed on unit circle such a way that the vertices are nothing but our nth root of unity. And we know that if you place a polygon on nth root of unity as vertices, then it is a n regular polygon. This we have already discussed in the last lecture. Now, the first identity which we are proving is, you consider the distance from p naught to p 1 and distance from p naught to p 2, and throughout for the other vertices distance from p naught we consider, and take its product. Their product gives n. This we have to show. Though geometrically looks complicated, but once we write down in terms of complex numbers, it is very clear. It is an easy identity to prove. So, without loss of generality, we assume that these pk's are placed at alpha power k, that is the nth root of unity, k is from 0 to n minus 1. Now, recall the identity which we already mentioned as a remark, that is our polynomial. If you recall this identity, z power n minus 1 can be factored as z minus 1 product with z to the power n minus 1, z to the power n minus 2, and thus polynomial can be factored as z minus alpha power k, where alpha k is nothing but the nth root of unity. So, we observe that this polynomial roots are just the alpha power k, where k is from 1 to n minus 1. So, we are going to recall this identity. What we have is z to the power n minus 1 plus z to the power n minus 2 plus z plus 1. This is written as product of, we have seen as factorized by its roots. The roots are, here we can say pk, or our usual notation alpha power k. Now, this identity is true for all complex numbers. Just choose z equal to 1, then left hand side we have n terms, we get n, and right hand side we get the product of k from 1 to n minus 1, 1 minus alpha power k. We are close to the identity which we are interested to prove. Now, ask yourself, what is this quantity? 1 minus alpha power k. 1 is our first nth root of unity, and k equal to 1 is the, with the angle which is 2 pi by n. We will get here this angle is 2 pi by n. This p1 is, we have written now alpha 1, p1 we have written it as alpha, and p2 we have written alpha power 2. Now, if I take the absolute value, then it gives the distance between p naught, which is 1, to pk, that is alpha power k. So, we see that if you take the absolute value for this identity, we get our desired identity, that is the absolute value of this product k from 1 to n minus 1, 1 minus alpha power k, and right hand side is a non negative number. Absolute value gives the modulus value gives the same. So, modulus of z1 z2 will give us mod z1 product with mod z2. So, which means that this is same as product of k from 1 to n minus 1, product of the modulus factor 1 minus alpha power k, which is equal to n, and this is nothing but distance from p naught to pk. This is p naught p1 product with p naught p2 till distance between p naught to p n minus 1, we get n. So, which proves the first identity. Now, we would like to prove the second identity, which is sin pi by n, product with sin 2 pi by n, and so on. The product value is n by 2 power n minus 1. To prove this, we need to simply calculate what is the distance from 1 to alpha power k, which is exactly going to get our sine terms. Let us calculate distance from 1 minus alpha power k, which is 1 minus, let us consider its square, this is 1 minus cos 2 k pi by n minus I sin 2 k pi by n whose mod square. We get it as 1 minus cos 2 k pi by n the whole square, that is the real part square plus imaginary part square, 2 k pi by n square. Once we expand this, we get a term cos square and we have a sin square term that gives 1, and we have one more term 1 here. So, together we get 2 minus 2 times of cos 2 k pi by n. Now, further you use the identity, that is 1 minus cos 2 theta can be written as 2 sin square theta. So, we get this is 2 times of 2 sin square k pi by n. Now, notice what is the value of k? K is from 1 to n minus 1. So, we calculated 1 minus alpha power k square is 4 times sin k pi by n square with k ranges 0 to n minus 1, excuse 1 to n minus 1. So, this implies that the distance between P naught to P k is given by 2 times of modulus of sin k pi by n. Since k ranges from 1 to n minus 1, now you see the argument here, the value varies from 0 to pi. So, the k pi value is pi by n to n minus 1 pi by n, which is certainly less than or equal to pi, and similarly this is greater than or equal to 0. Under this argument, sin value is always non-negative. So, we get the value which is sin 2 times sin k pi by n, which is nothing but the distance from P naught to P k. Now, use the previous proved identity which gives P naught P 1, which is 2 sin pi by n product with 2 sin 2 pi by n and product with 2 times of sin n minus 1 pi by n. The product is n. Hence, we see that product of sin pi by n, sin 2 pi by n till sin n minus 1 pi by n, we get n by 2 power n minus 1, which is the required identity. So, we have proved the second. To prove third identity, I will just give the hint. What we have considered, so let us go back to the identity which we would like to prove. We get here sin pi by 2n. The previous identity we have sin pi by n. So, to get this particular term, we consider 2n regular polygons, apply this identity. So, which means we take number of n being 2n. Okay. So, twice of given n, you consider that as a regular polygon and then use this identity, and with the minimal manipulation we can prove the third identity. So, I skip the proof. So, in this lecture we saw several propositions based on nth root of unity and some problems we have solved which is on the nth root of unity, as well as we saw nice trigonometric identities which we are able to prove using the nth root of unity. In the next lecture we will discuss more problems on this. Thank you.